Hello, my name is Harrison and I'm here to talk about bells. No bells. No, just forget it. Sorry about that. I'm here to talk about bells, decibels. So, when we're given a value of decibels, we need to find out a certain proportion to it. Normally it takes a pretty complicated calculation that you can't really do in your head. So, what I wanted to think of is, how can we best estimate this value without a scientific calculator? So, when you're estimating decibels, there's a few different levels of approximation that you can go to. So, what I decided the first level would be just recognizing that an addition of 10 dB results in 10 times the value. So, for this example, we could say that because there's 90 dBs, we know that it's going to be approximately in the order of 10 to the 9. And so that's just the first level. And then the second level, you can also recognize that plus 3 dB is very close to 2 times. So you could estimate that this is 2 times 90 dB, or it has a coefficient of 4. So you can estimate that it's 90 plus 6 dB, or 4 times 10 to the 9, which you can see is pretty close to our estimate here. And so the next level is what I call power of 2's estimation. So basically the question is, what if you don't have a decibel value that's a multiple of 3? One answer to that you can see that the multiples of 3, they contain every single digit. There's 1, 2, 3, 4, etc., etc. So you can use this fact to express any integer value in terms of a multiple of 3, as well as subtracting a certain number of 10s from it. So for example, you can express the number 4 as 24 minus 20. And when you bring this equation out of dB, you can express it as this equation right here, where the multiples of 3 are expressed as powers of 2 because of this fact right here, and where the subtractions of 10 are expressed as divisions of 10 because of this fact right here. So, using this fact, we can say, for example, if we had 28 dB, we can say 20 plus 8, and we can express this 8 in terms of this guy right here, 18, because 3 times 6 is 18, minus 10 is 8. So 3 times 6, 18, minus 10, this gives you 8. And then again, we bring this equation out of dB, and we can express this 3 times 6 as 2 to the 6, 64, and 10 times 1 as 0.1 because it's negative. So then we can estimate that 28 dB is approximately 640. So I put all of the different options you could have into a table. So here are all your dB values. Here's the little code you can have. This is basically just the multiple of 3 that's associated with a particular digit. So for example, the 7th multiple of 3 is associated with 1 because it's 21. The 4th multiple is associated with 2 because it's 12, and so on. So here's all of the intermediary calculations, but this is mainly what you're looking for. So this is what you're estimating this dB value is that this is the value that goes with each of these dB values. So we can estimate, for example, that 8 is 6.4, just using the same logic. And then if you look here, here's the actual dB values. And if you do the error calculations, you can see that the rounded error is about a maximum of 2%, which isn't too bad. Additionally, if you are given a dB value that's between two integers, then we can use a little fact of logarithms that allows you to assume it's linear. Because you see here on a large scale where you're operating on tens of dBs, it's very curvy, it's highly nonlinear. And then medium and small scale, it's getting more and more straight, but at small scale, it's basically linear. So for values right here, we can basically just interpolate between the value associated with 32 and 33, and it'll be 58% of the way from 32 to 33. So here's that calculation right here. You can see the linear interpolation. Here's the 30 dB. And we basically can just see that we get an estimation of 18,032, which is pretty close. Also, as a little bit of a side note, I did some error analysis on the interpolation method. So the peak error is about 2.49% at a value of about 7.34 dB. And some interesting things about this graph, you can see that it always has minima at the integer values. And then here you can see the interpolation error as it goes through the interpolation. This is just a sketch, but if you would like to see the math to make this, it's on a Desmos script with the code ERJ2QPJQQY. So that's all of the estimations out of the way. So here's some practice problems that you can go through. If you'd like to solve them on your own, just pause it real quick, but I will go through all the work in just a few seconds. So for this first problem, basically the first step you want to do always is just break it down. So we can see that this is 30 plus 7. The 30 contributes a kilo, and then the 7, which multiple of 3 gives a 7? That's 3 times 9. So 2 to the 9 is 512, or 5.12 when you correct it. So we can see that we can estimate it as 5.12 kilowatts. And if we get out the old calculator, you can see 10 to the 37 over 10 will give you just about 5.12. Alright, so now for problem number 2, we can see 72 dBm. You're going to break that down to 60 plus 10 plus 2. So the 60 is a mega, or 10 to the 6. The 10 is a 10. And which multiple of 3 gives a 2? That's going to be 3 times 4, because 3 times 4 is 12. 2 to the 4 is 1.6. Well, corrected. And so we can see that it's going to end up giving 16 mega, and then milliwatts because we're using dBm. So the milli and the mega cancel out, and you end up getting 16 kilowatts. And you can double check that on your own. And so for the 19 dBW, again, you just break it down, 10 to 9. The 10 gives a 10, and the 9, that's 3 times 3. 2 to the 3 is 8, 80 watts. And here are some of the problems that require a little bit of extra tricks, if you will. So we've got negative numbers here. So what you want to do for the negative numbers is go to the next smallest power of 10. In this case, the next smallest power of 10 is going to be 10 to the minus 3 or milli. And then it's just 1 dB above that, which which power of which multiple of 3 is associated with 1? That's 3 times 7, 21. So 2 to the 7 is corrected is 1.28. So 1.28 milliwatts. And similarly for this example, break it down to the lowest power of 10, minus 60 is micro, plus 10, and then which multiple of 3 is associated with 4? That's going to be 8, 24. So 2 to the 8 is 256, corrected is 2.56. So that's going to end up yielding a 25.6 micro. Micro and milli combined to get 25.6 nanowatts. And then we can double check that real quick. If we just do 10 to the minus 29 over 10. And you see we get a very similar result. Oh wait. Wait, that's the wrong one. Hold on. 10. That does double check that one too. So minus 49 over 10. There we go. In engineering form, 25.6 nanowatts isn't too far off. Alright, so then for voltages expressed in dB form, you have to be really careful because dBs only express changes in power. So when you're expressing a voltage, there's an extra squared term that expresses itself right here. So you get 20 instead of 10. So if you want to use all the same tricks, basically all you have to do is preserve this 10 log term by dividing both sides by 2. So all you got to do is divide your dBV value by 2 and perform the same operations as before. So this is going to be an example of interpolation. We know that the value is going to be somewhere between our estimation of 7 and 8. So here's our estimation of 7 and 8, and we're interpolating halfway between, and that ends up getting 5.76. And if we double check that guy too, you can see 10 to the 15 over 20. That will give you about 5.76. And then for this final question, minus 4, because you're dividing by 2, then you're expressing it as the lowest power of 10 as possible. So, milli plus 100 plus 4, because of the 6, which power of 2 is associated with 6, or which multiple of 2 is 2 times 3. So 2 to the 2 is 4, 400 millivolts. So that's basically all I wanted to show you guys. I thought it was kind of interesting. It's very cool how there's some patterns here. This is basically just like the powers of 2 organized by coefficients. It's a very interesting thought experiment at the very least. And I think it's nice to just be able to organize dBs into some sort of system rather than just memorizing a list of values. I think that's much more interesting. So I hope you guys enjoyed and got something out of this. And if you have any questions, let me know, and I'll see you around.